Awesome. Okay, so today I thought we'd talk about JASP, which is kind of like an SPSS alternative, also an alternative to R that's a little bit easier, more user-friendly, especially when you're like first starting out. And it's similar to SPSS, but it's free, which is awesome. So I'm gonna share my screen. Oh wait, you have to enable it.
Sorry.
Literally every time though I do that as well. Okay.
All right.
Okay, so this is, wait, what do you guys see?
Your screen.
JASP? Why am I so bad at Zoom still?
Same.
Okay, you see JASP?
Yeah.
Cool. Okay, so this is the site. So I will send this in the RA chat. So if everybody wants to download it, it's really not very big, so it shouldn't take too long. And then you can kind of follow along. I'm going to use the same data set that we used for the previous tutorial, so I'll also send this. And if you want to, if you got rid of the data file, you can just click download again. So yeah, you just click download zip and then save it to, I'm going to save it to the desktop just so that I can access it easily. Okay, so also bear with me because I have never really used JASP until yesterday, so hope that it works easily. Okay, so I'm going to open it. And I played around with it yesterday for a little bit, so I think it should be okay. Okay, so you basically want to open your data set. So I'm going to open the data that I saved from GitHub here. And then it imports it. And so you can see that it's, if you've ever used SPSS, it's pretty similar to the way SPSS looks with the variable types and the data frame. And it's pretty nice because you can edit the type of variable. So it seems like it's doing pretty much the right thing, as in it's making these percentiles scale variables, but you can also change that if for some reason it imports it as the wrong type of variable. So like sex and group are nominal variables. And then it's kind of cool because you can change this label here, which will be nice when you are making charts. I'm just going to change those variables. Yeah. Okay, and then the next thing that you do is these are all of the different types of things that you can use up here. So the first thing I'm going to do is just do some descriptive statistics. And so basically this is kind of, this pane here is kind of like your output pane, and this is your input pane, kind of similar to R a little bit. And then you can toggle back to your data with these like side button things. So then if you want to look at different variables, you have basically all the ones that are available here. And then if I wanted to look at anxiety, I would put it here. And then that already is basically telling me the output here. So it's saying I have 100 participants, 0 missing, with a mean of 64 standard deviation, minimum and maximum, or the whole data set. And then if you want to look at the difference by groups, which is what we're usually looking at when we're looking at early stress versus comparison, you just basically drag this group variable to the split, and then it automatically splits it here for you. So you can see the mean of each group. And
That's mean depression score?
This is anxiety percentile.
Or mean anxiety score?
Yeah, yeah. And then you can add plots here. So I'm going to add a box plot, which is like what we did with R in the last tutorial, so we can kind of see how that looks. So here it is. You basically just click it and it comes up, so it's super easy. And that looks really similar to, so if we look back at the box plot, that looks really similar to what we made in R. And it even has this ggplot color thing. So you can pretend like you made it in R. Yeah, so it's pretty simple. There's a lot of different little like features you can add. So if you wanted to add, like to look at your distributions, it's kind of weird for a box plot, but this shows like how many participants, like you have a lot of participants here, and it gets kind of fewer as you get to the top. Jitter doesn't really, oh, jitter, that's nice. So that shows each of your participants individually, so that's kind of cool. Yeah, you can like label outliers. I don't think we have any outliers in this one. And then you can kind of see like your basic histograms as well, which is nice when you're doing things like t-tests, because the assumptions of a t-test are that your underlying distribution is relatively normally distributed. So this is kind of nice. You can see like this looks pretty normal. This sort of looks normal. Not really though, which is kind of interesting because I actually generated this from a normal distribution, so that's pretty weird. But it's random, so there's always a chance that you get something a little strange. Yeah, you can add like a density curve. Some of these probably won't really make sense for what we're looking at. But yeah, so these are all just like descriptive plots. You can add, oh, that's nice. You can add like the median to your table, the mode, the sum. And then, yeah, you can look at like your distribution and see how skewed it is. The kurtosis, which is like the pointiness of the shape of the distribution. So that's pretty nice because you can just click these buttons and it kind of calculates all this stuff for you. So this is like the descriptive part where you're plotting things and looking at things. I'll just show you one more type of, so if you wanted to look at more of like a scatter plot type of thing, of like anxiety and depression, then you could look at this. So this is a lot going on right now, so I'm just gonna kind of remove some of that. So basically now that I added depression here, it's showing me these same charts, but for depression and anxiety. So I can see all of my histograms with their shapes and their density curves, and they all look pretty normal except this one, which is good. And then the charts that I made separated by group with all of those summary statistics that we were looking at. And then if you're looking at two variables, you can look at a scatter plot, which is a little more appropriate for two variables. I don't know why it's so squashed in the corner. But this is basically plotting anxiety and depression together. So, and then it's separating them by the group. So like if I took this group out, we would now see that this is just how does depression move with anxiety. So as anxiety decreases, what does depression look like? And so you can add a regression line. So here, this is like a smooth function, but normally you might want to do a linear function. So here you can see that like as anxiety is decreasing, increasing, depression is also increasing. This really isn't very solid correlation. I didn't make these correlated when I made this data, so that makes sense. In real life, I would feel like anxiety and depression are probably a lot more correlated than this. And then you can add your 95% confidence interval. So that's basically this ribbon around the data. And you can see that it gets really narrow in the middle here where we have a lot of data in this range, and then it kind of fans out a little bit towards the end where we have less confidence in our prediction. Yeah, and then if you wanted to look at that by group, you would do what we did at first. And I still have no idea. Wait, oh, okay, wait, there we go. Okay. And so this is really cool when you're looking at interactions. So you're looking at, when you basically are looking at 3 variables, you're starting to look at the way they interact. So you're looking at anxiety, depression, and group at the same time. So you're looking at, does anxiety have a different relationship with depression based on whether you were comparison or ELS? Here, it looks pretty much the same. The fact that we have these groups, you can kind of tell that like the mean, see how there's like a lot of blue dots to the right and a lot of red dots to the left? That's kind of just showing you that on average, the ELS group has higher anxiety than the comparison group. And similarly, how there's more blue dots kind of at the top than, and there's more reddish dots at the bottom, also kind of tells you that the ELS group has a higher level of depression than the comparison group. But see how the lines kind of look the same? So there probably is not any interaction between group and this relationship based on this data. Because if there was, you would expect like maybe the lines to be crossing or something like that, doing something really different depending on what group they're in, the pattern overall. Yeah, so that's pretty cool. Yeah, as you can tell, it's pretty simple. It's really like a point and click kind of interface, which is nice. And then you can do tests too. So if we wanted to add a test, so say we wanted to do, like we did in our an independent samples t-test between the 2 groups for anxiety. So independent would be like we have 2 separate groups of people, ELS and comparison. Paired would be like if we had the same people over time, like we had some kind of treatment and we wanted to test before and after the treatment. One sample is if we're just seeing if there's a difference between that group and 0. Doesn't really make sense in the context of anxiety because you wouldn't really expect anxiety to be 0. You might though could test it against the average. So if you thought that we have percentiles, so if you think that the average is a 50th percentile, we could test and see, is the ELS group, is this 77 or 63% percentile statistically significantly different than 50, which is the average. So you could do that. That would be like a 1 sample. But if you have 2 groups, you're going to be doing like a 2 t-test, 2 group t-test. Okay, so this is like the second part of JASP, is that each thing you add becomes like a little drop-down thing here. So like this is all of my descriptives, and I can like duplicate it, or like it just tells you about it, tells you about all the different things. You can delete it. And then the next part that I just added was where I'm going to do this test. So now if I want to test the anxiety by group, I can do my t-test and it comes up right there. And you can see that it is significantly different. The 2 groups are significantly different, which is what we found in R. And let's just flip. Yeah, see, it's basically giving you the same information there. With the t statistic being negative 8.814. Yeah, and it's using a slightly different, this is using a simpler calculation for the degrees of freedom where it just subtracts 2 from the population size. This, I think, is using a slightly more complicated system. And then this one's just giving you this p-value as less than 0.001, whereas this one's giving you the exact number. But you can see that it's definitely less than 0.001. So yeah, and then what else can you do here? You can choose like what kind of test. So this is called a student t-test from the person that invented it or came up with it or something. Then you can decide what kind of hypothesis you're testing. So this is a 2-tailed hypothesis. We're basically saying that we think that there is a difference between group 1 and group 2, and we're not specifying which direction we think it is. Like, we're not saying that we think that the ELS is going to be higher. We're just saying we think they're not equal to each other, which is a little more conservative of like a statistical estimate, which is good for like being conservative and not making claims that might be like false positives. But you can also do a one-tailed test where you test if group 1 is bigger or smaller, and that basically just kind of inflates your type 1 error rate a little bit because you're increasing your confidence. You're increasing it to like, it's like a 10% instead of 5% rate if you do that. You're like getting rid of one of the sides. Yeah, you can do like a normality assumption, which is cool. Yeah, so this is basically showing, so for normality assumptions, you want it not to be significant, because basically if it's significant, that's saying that your distribution, underlying distribution, is not normal, which is not what you want when you're running this kind of like parametric test. So you can see that for the comparison group, it's not significant. So we can pretty much see that here. This looks pretty normal. It actually is significantly different from 0 for the ELS group, which we could already see when we look at this, because this doesn't really look normal. We kind of knew that that was going to be violating that assumption a little bit.
You know, it's not significant because the p-value, right?
Yeah, so it's not less than 0.05 for this. It is for this. So that's basically telling me that that distribution underlying is not particularly normally shaped. Yeah, then you can check like the variance, equality of variances, which basically just means like, is the variation in the data the same for both groups, which you usually want it to be the same. This is not that similar, but it's also like pretty close to not being significant. So this is something you want not to be significant either. It's also going to be really difficult though for these for a really small data set like we have for MBB so far. So I wouldn't worry too much if these assumptions are not met for the purpose of your projects, just because we have so small amount of data that it's probably not really gonna be normal. Cool. And I think that's pretty much everything. I mean, you can do a lot of fancy stuff in here. You can do a regression. You can do, so let's do this. Okay, so let's do correlation between anxiety and depression. So we can see that the correlation is I don't know, yeah, 0.2 between them. Yeah. Oh yeah, okay, this is like a correlation table. So if we had more variables, there would be like, yeah. And yeah, it actually is significant, which is kind of surprising given that it doesn't look, I mean, I guess both of them are going down. So I guess, but yeah. And then you can do regression, which is cool. So if I wanted to like see how anxiety and group contributes to depression, I can do this. So I can see that, so these are like the coefficients for the regression. So I can see that on average, with all other things held constant, group being in the ELS group makes you about 15 points higher on anxiety. And this is like really significantly, this beta is really significantly different than 0. Here, when I add group, anxiety is no longer really a significant predictor of depression. So we can see based on this would be saying that basically on average, as you go up one level in anxiety, you go down 0.08 points on depression, but it's not significant, so it doesn't really mean much. So basically this is saying that like most of the lifting that's going on in this equation is due to the group, not to the anxiety, if that makes sense. Yeah, and I think you can even do like interactions here. I think you like hold these two down or something. I don't know. Oh, I just crashed it. Thing. I think you can do some kind of interaction. Oh, I got rid of all of it. But yeah, I mean, I think that's basically all you guys are going to need to know for the purpose of your projects. Most of you will probably be doing like ANOVA or t-test. Yeah, do you guys have any questions or anything you want me to show or explain?
Yeah, you think you did the t-test. You did the ANOVA. Can you do the ANOVA?
Yeah, so here we have, well, we only have 2 groups. We can do it by age. Let's look at age.
And the ANOVA, man, I don't remember that much from statistics, but ANOVA tells you what again?
ANOVA tells you, it's basically like a t-test, but when there's more than just 2 groups. So if you had like 3 groups, we had like an ELS, a comparison, and another group, and we wanted to see if any of those 3 groups were different on anxiety or depression, then we would do an ANOVA. We only have 2 groups. We could do,
So you wouldn't use an ANOVA if you only have 2 groups? Like my study, for example, has transfer and non-transfer, so I would use t-test only?
yeah, you would probably use a t-test because you only have 2. I don't even think I can. Yeah, because they're not categorical. You could do an ANOVA with age if you put like each person into an age, each age as its own group, or if you grouped ages together, you could do like children and adolescents, and then you could do, well, that's only 2, but if you had like 6 to 8 and then like 9 to whatever, you could do those groups. It won't let me because it's not a categorical variable, and we don't have any others with more than 2 groups, so we can't really do an ANOVA, but basically the same kind of thing as a t-test, just with more than 2 groups.
So a t-test will tell you if the difference between the 2 groups is significant or not. And so does a ANOVA, but it'll be more than 2 groups.
Yeah. Okay. Basically when your input is more than 2 groups. I'm really terrible with ANOVA though, because I've never really done ANOVA. You know, I prefer like regression and such, but Ryan always makes fun of me.
In Psych 100B, I did like a 2-way ANOVA or something, and I thought I had 2 IVs with 2 levels, but I thought I was picking the ANOVA because I had 2 IVs. Like, so for example, in Psych 131 with Bridget right now, we have to pick which test that we want to do, and I thought it was ANOVA because we had 2 groups, but
2 groups, yeah. Anyone? No, I mean, if you have 2 groups that you're like splitting on, it's definitely, you don't need ANOVA. I'm not sure if you have more than 2 outcomes. I think that would just be multiple analyses because you can only have 1 outcome. So I don't think you would do an ANOVA there either. Is anybody else like an ANOVA expert? Oh wait, I can't hear you. I think you're muted.
You're muted. Yeah.
Sorry. Do ANOVA. If you have 2 groups with 2 levels, you technically have 4 groups, so you can still use ANOVA.
Yeah.
So if you have like gender, like male, female, and then something else that's 2 levels, it'd be like, you could say early stress comparison. So you have male, early stress, male, comparison. So it's 4 groups in total.
Here we go. Yeah. Okay. Yeah. Because we have 2 groups. We have sex and group, so we can do it. And we can see that there is an effective group. There's not an effective sex, and there's not an interaction between sex and group. I think.
Yeah, it would be really useful. I'm just thinking how I shouldn't have thrown away my stats notes.
Yeah. I mean, there's a lot online though for like this kind of thing. I also have really good notes that I could share. I was telling Kristen about for my intro stats class. They're like amazing, but I have to get permission to see if I can share those. But yeah. Oh, sorry, Nicole, you missed how was your midterm?
You know what? We sometimes you have to lose a battle to win the war. So this may be a lost fast battle, but it doesn't mean a lost war.
That's good. That's good. I think they're going to be lenient, right, with the grading this Corona season.
I mean, I hope so. Like, just I did my best effort. Is all I could ask myself for. I'm gonna go drink a mimosa afterwards. So life is great. Friday's here. I am not unhappy.
Yeah. Oh, I guess one other thing to just notice that when you do a t-test instead of a t statistic, you have an f statistic. So that's how you're calculating. That's how the software is calculating the p-values based on this f statistic. And when things are like multiplied like that, that means interaction. So does the relationship between, or does anxiety depend on like sex and group? So is it different for each group depending on their sex, or is it different for each sex depending on their group? That's basically what like an interaction would be. Yeah, I was like, I don't get ANOVA, and Ryan was like, it's just like regression but with nominal variables, and I was like, what? So sorry, I have to touch up on my ANOVA before we go over that again. But it is kind of the same. Let's see. Okay, let's do a regression where we do, well, that's exactly what we just did when we did our covariates, our sex and group, and our outcome was this. See, this is basically saying the same thing. That group is significantly it's like a significant predictor of anxiety, but that sex isn't. And then this is what I was trying to do with my interaction. So if you wanted to get this interaction, you would just interact these. I'm scared to do this again. Oh my God. Well, that's basically it. You get the same thing.
What happened?
Oh, it keeps like crashing. Wait, somebody Google for me how to do interaction and JASP regression. So I swore I looked it up yesterday and it said that's how you did it. I'm not gonna try it. Does anyone find the answer?
Looking.
That was scary.
Can you try shift, Emily? I know with SPSS, when I do shift and I hold both the variables together, then they'll make the interaction when I drag them to model terms. But I don't know about JASP.
It probably is because I think it's similar to. Ah,
Yeah.
yay! Yay! Okay. So yeah, now it's showing the exact same thing as the ANOVA, but with regression. It's showing that there's no interaction. There is no real effect of sex, but that group is a significant predictor of anxiety. So ANOVA is just like regression, but with categories.
Also, one thing with ANOVA, like the language is different too. With regression, it's a predictive model. ANOVA is just significantly different means. So just like the way you talk about it when you're trying to choose which test, I'd just be careful with that.
Yeah, I have no idea how to talk about ANOVA, so don't listen to anything like that. But yeah, it's kind of cool because it's like pretty much the same thing, except for that it doesn't tell you when you're dealing with, and correct me if I'm wrong, but it doesn't tell you which group is different, right? It only tells you that there is a difference.
Exactly. So then you want to go into your descriptive statistics, and then you can see the means, and you'll figure out based on that which one has a higher or lower mean.
Right. Right. So it's telling you basically that there is a difference between the groups, but that we don't know which one is different. So we need to look at the means.
Mm-hmm.
And then we'll see which one is different based on the group.
Exactly.
Yeah. So we can see that this one's higher. Yeah. So that's pretty cool. I don't even know what all this means. Some kind of calculation on something. Yeah, so yeah, any other questions? Does anyone have, do you think JASP is, have you guys used JASP before? Has anyone used it? I haven't either, but it's similar to, I haven't really used SPSS either. It's pretty similar, right?
Yeah.
That's good. Yeah. I think it's supposed to be based on that. And you can also do Bayesian stuff, which is kind of cool. You can do the Bayesian version of everything that you can normally do, which is pretty cool. So that's like the Bayes factor, and then I guess this is kind of similar to the p-value. I'm not really sure what this is. But yeah. Cool. Well, that's all I have for y'all. Nicole, I'm sorry, I'll have to go over it if you want to see it. Although it's really easy. You should just like kind of play with it and see if you can.
Is it easier than R? R is putting my hair in all directions.
It's 100% easier.
Okay, cool.
Yeah.
I'm excited.
Also, we recorded this, so you can watch it.
Okay. Oh yeah, I'll definitely do that. But
I feel like it's just like the knowing the terms and stuff, like what they mean and
Yeah.
all that.
Yeah, the interpreting the output is a little bit complicated. But it would be like that on SPSS too. I think these outputs are like almost exactly the same.
Mm-hmm.
So yeah, really what you're looking for is like your test statistic, which is like your F or your T or your beta weight in a regression. And then, which is like your slope, sorry. A beta is like the slope of the line that you're calculating. And then your p-value. You don't really need to know a lot of what this other stuff means. This is more like what goes into the calculation of your test statistic and your p-value.
What about degrees of freedom? I've never been able to grasp what degrees of freedom is.
Yeah, so that's like based on your sample size, and it's like it adjusts a little bit, I think, for the estimate that you're making. So like if you have two groups of 100, you like subtract 2 from 100 to get your degrees of freedom. I don't think it's not that important to know exactly what it is. I'm not really sure exactly what it is, but it's just something that they use in the calculation to make your estimate like a little more conservative so that you don't inflate your false positive rate. But you will rarely have to calculate a degrees of freedom yourself unless you're doing it by hand, which you probably won't be doing if you're using any kind of software. And I guess the other thing is just like all of this stuff, which is like goodness of fit measures. So like your R squared is like how well does this model fit your data? Also not super important for the purposes of what y'all are doing. But yeah, that's another thing to note.
R is the correlation coefficient.
Lowercase r is Pearson's R is the correlation coefficient. R squared, maybe it's related. I don't know. Is it related? Does anyone know?
No.
Might be, because regression is correlation. You know, like a regression between two variables is the same as correlation.
I think R squared is PRE.
Is what?
The PRE value.
What's PRE?
Oh, it's like the percent explained by the
Yeah, percent of variance explained.
yeah.
It's some kind of goodness of fit measure, but it could be related to Pearson's R because they are kind of related. So I don't know. We'll have to find that out. Yeah, I think that's it. Anything else? Y'all are all laughing, so I guess.
I'm just sorry. I'm messaging. I'm not gonna say who from this lab, but I messaged him like, what is a PRE? There's so many terms that I have no idea.
When I was in my first lab, like they used like the most complicated terms, and I had absolutely no idea what anyone was talking about. Like I remember, like at one point, the professor, it was like I was in the lab, and the professor turned to me, and she's like, "Everyone knows what Raven's matrices are, right, Emily?" And I was like,
All right.
I was like, absolutely. In my head, I was like, I have no idea what a Raven's matrix is.
Absolutely not, professor. Not everyone knows.
Literally, that's the way she said it. She wasn't like, Emily, do you know what a Raven's matrices are or whatever? She was like, everyone knows what Raven's matrices are, right, Emily? And I was like,
Right.
Yeah.
Do we need to know that? Is that something?
It's just an intelligence test, I think, right? It's kind of related to the WASI, why it's like those little patterny things where you choose the one that goes next. So I don't know why everyone would know that, but
I feel like it's just been so long. Like I remember hearing about degrees of freedom and R and like sum of squares and all these things, but do I remember what they mean?
yeah, exactly. That's also really bad because they name a lot of things the same thing. So like the beta, I remember this, I was really confused about this, like the beta value, I think is sometimes one of the error rates, like the type 1 error maybe is also called the beta rate or something. But then, yeah, but then the coefficients of a regression are also called betas, completely unrelated to beta type 1 error rate. And so I remember like, I was also sitting in my lab once and they were talking about betas and I was like, what? I was like, why are
What's wrong with us just calling it, I don't know, error rate?
There's so many error rates to that. There's like standard error, there's like variance, there's standard deviation, like there's some error thing, confidence intervals. Yeah, that's a bad one. But yeah, just like play around with this. It's pretty simple, so I think it'll be good if anyone's not feeling the R. Although I highly recommend R if you're gonna learn it. But maybe not for like your first ever project. And I think
Not have like something due in like 8 days.
yes, not for something due in 8 days. Alyssa, if you ever do the one where you're looking at the time, you'll need to do this like repeated measures. ANOVA.
Yeah, I'm definitely going to be hitting somebody up.
Yeah. I mean, for most, I think for everything, y'all can pretty much do a t-test or an ANOVA. But ask Chloe or Kristen about ANOVA.
Also, if you're doing like, let's say you have multiple dependent variables and the same independent variables you want to use, as long as those dependent variables are correlated but not really correlated, you could do a MANOVA. So there'd be less error introduced into it, or you need to adjust for multiple comparisons, which is a post hoc Bonferroni test. But just so you don't like do 10 t-tests or 10 ANOVAs, it's going to be problematic. So you might want to choose like a MANOVA or adjust with Bonferroni correction after each one. Super important.
Yeah, that's a really good point because as Nicole discovered in her fake data set that she actually found a significant difference using a t-test in her fake data set that I pulled from a normal distribution that was not different. That just goes to show that for like every test you run, you introduce more chances of finding an effect that's not actually there. That's just due to like noise or chance in your data. So like Chloe was saying, you want to correct for that. So every time you run an additional t-test, you want to basically like, can't remember the exact calculation, but you like divide your p-value by something. So your p-value, the significance threshold gets smaller and smaller for each additional test that you run. So it would no longer need to be 0.05, but it would need to be like 0.001 or something. I can't remember.
And in like SPSS, it's point and click. Like to apply a Bonferroni correction, you don't even need to do the math. You just need to like, it asks a few questions, you enter things, it does it right away. So it's super easy.
Oh, that's good.
You love SPSS.
I love SPSS. I know.
What a Bonferroni correction is. My TA said that all the time. I don't know. I didn't doubt that. There was a whole quarter of not knowing what Bonferroni was for. Thank you. You should be the 100 BTA. Absolutely.
Yeah.
Please.
They have it here, so that's good. Yeah, so the more you can kind of put into one model, the better because it kind of controls for all of those things. Just like you wouldn't want to run like 6,000 different like t-tests or regressions or something. You also probably don't want to run like 7 ANOVAs with like a bunch of different dependent variables, so you could use the MANOVA, right? Which does that mean like multiple dependent
Exactly.
variants?
Wanted to look at depression and anxiety for both group and sex, you could do that. You just need to check you know how you did the correlations? You just need to make sure that they're correlated, but not too much so. It's one of the assumptions underlying MANOVA. And if that's the case, then you can easily run it and it will give you different outputs for all of that. Instead of doing 2 ANOVAs, you just do 1 MANOVA.
Let's try it. So we do anxiety, depression, and
I don't think they were correlated though, so I'm not sure if you'd be able to do it.
anxiety and depression have to be correlated?
At least in this data set, yeah. I remember only one was, they had pretty low, it was like 0.2, which is a very small correlation.
It was. So then, oh, I guess this does it.
Give it a try, yeah.
You try? So what is the, oh, so this is just telling me if there's a difference in any. It doesn't specify which one, right?
And there should be a follow-up where it will give you, it'll generate the overall MANOVA, and then it should follow up with individual ANOVAs that are adjusted with correction for it, but I don't know why it didn't.
Ooh,
There you go.
yeah.
It usually just, it self-generates on SPSS.
Oh, cool. Oh, that's pretty cool. Nice.
So you'd report the MANOVA statistic, and then you could say each of the ANOVAs, and they've all been adjusted following the MANOVA, so it makes it pretty easy. So you have 3 test statistics that you'd be reporting.
Yeah. So how should you phrase this effect of group?
I'm trying to think off the top of my head. I can pull it up from one of my thesis for my master's. I used MANOVA a lot.
Well, you guys notice that like statisticians are very like picky about how you phrase things, and you get in lots of trouble if you're like say something and they're like, no, that's not.
Totally.
It's like one word, and you're like, and you're like, cool.
I can't think off the top of my head, but if anyone's interested in using MANOVA, which I would recommend, just like I can just like slap me and I can give you the exact terminology that you use, but you would first report the MANOVA statistic and then you would say the individual ANOVAs. See if I can find it easily. Like going
so
through.
you're just saying that there is a difference in one of the outcome variables based on one of the input variables. One of the, do you even call them, you don't call them independent variables though if they're,
No.
they're
So, let me see, hold on.
factors? Yeah, probably factors. Yeah, fixed factors. Based on one of the groups or something.
Okay, so there's different test statistics you can report from ANOVA. For mine, my data wasn't super normal, so one of the strongest ones to combating that error was the P-Lies trace. So I did a 2-way ANOVA with my variables being sex, so male and female, and then group, which was neurotypical, and then autistic. And then you'd say it yielded a significant main effect of group, and then you report the statistics. So mine would be P-Lies trace, which I guess this one just automatically did. And then you would do V, which is the letter for P-Lies trace, equals, and then you'd see here what it is overall, and then you'd report the F statistic that it has with the degrees of freedom. So we have 2 and 95, and then you would equals what the approximate F statistic is here. And then this one, they're
for each or just the P-Lie trace?
Just the P-Lie trace. And then the effect size is a different one. I don't know if it has effect size on here. No.
Probably another option.
Yeah, definitely something you want to report is effect size. That's super important. So you would put the P-Lies trace value, the letter F, the degrees of freedom, the F value, and then the P value, and then the effect size. So it's like a lot to report in one sentence. And then you have to report the ANOVAs after that.
That's a lot.
That's
It's
a lot.
Yeah.
That's a lot.
Yeah, I know.
Yeah, I forgot about effect sizes too, because they're kind of built in when you have a regression, because basically like, the effect size is kind of like the like number, the slope, like how big the slope is kind of your effect size.
Yeah.
It could be like very small but significant, or it could be like very big and significant.
Yeah. It's all about the magnitude of the effect. So it's really important to include that when you're writing about it, because it could be a really tiny effect, even though it's statistically significant. if it doesn't really matter in the grand scheme of things because it's such a small effect, then it's a significant finding, but it's not really a meaningful finding.
Yeah. And the kind of same thing with the t-test. Like if you just report the value of your t-test, like the p-value, then yeah, it could be really significant, but maybe the ELS group only has like 2 points higher in anxiety on like a 100-point scale or something, which like isn't really that much of like a meaningful difference. So that's something to think about too.
Have you guys heard of Cohen's d before as kind of like a standard for effect size? Yeah. So you can use that for a lot. I know ANOVA has its own kind of thing that's separate from Cohen's d, but related. But when you search the different types of tests, you can find out what the effect size they use for that test is, and then just report it based on their kind of like, under this amount would mean small, medium, large, and they'll give you kind of the range there.
Yeah. And there's effects for correlation too, right? Like it's like anything under like 0.3, right, is small. Anything 0.3 to point something else is medium. Anything higher than that is
0.8.
Yeah.
0.8 is large.
Yeah. It kind of depends on what you're doing. I don't see any effect size on this. Do you?
No.
Yeah.
No.
That's weird. Yeah.
That's weird.
We would have to look into that.
Yeah. Cool. All right. Well, it's 2, so I'll let you guys go, but hopefully this was helpful.
Yay, thanks, Emily.
Yeah, thank you.
Wait, before you all go, let me stop the recording.